Hi, this is Tammy McClish. Let's take a look at Section 2, X-rays, ionization, and matter. When we're taking a look at atomic structure, we need to think about matter. Matter is anything that occupies shape and has shape or form. It is the fundamental building block of matter of all atoms and molecules. Matter can take on the following forms. It could be a solid, a liquid, or a gas. When it's a solid, it has its own definite shape, it has a definite volume, and a definite shape. When it's liquid, it takes the shape of its container, it has a definite volume, but no definite shape. And when it's a gas, it has no definite volume and no definite shape, but it does fill all available shapes. Let's think about a 20-pound bucket of water. You may freeze it into a 20-pound bucket of ice, or it may evaporate into a 20-pound bucket of water vapor. So the form of matter may change, but matter remains the same. Even with these particular examples, it always remains the same. Mass is the quantity of matter that makes up any physical object, and our mass is our weight. And as you can see, dependent upon if you are on Earth, the Moon, Jupiter, Sun, these will change depending upon your location. Definition of atom. All matter is composed of fundamental building blocks called atoms. The fundamental particles of an atom are an electron, a proton, and a neutron. The electron has a negative charge, elementary particles with one negative charge, electrons surrounding the positively charged nucleus, and determine the chemical properties of the atom. A proton is positively charged. An elementary particle with a positive electron charge equal to that of an electron, and a mass approximately equal to that of a neutron. A proton is located in the nucleus of an atom. And a neutron has a neutral charge. It's an uncharged elementary particle with a mass slightly greater than that of the proton, found in the nucleus of every atom, heavier than hydrogen in the nucleus of an atom. And when you have a neutral atom, you're going to have the protons equaling the neutrons. Protons equaling the electrons, giving you a neutral charge or no charge whatsoever. Some more definitions. When we take a look at the nucleus, it is the center of the atom containing the neutrons and the protons. Shells are the orbital energy levels surrounding the nucleus of an atom. The shells contain the electrons, and the most important shell in radiology is the K shell. And this picture shows you the different shells, their symbols, and their maximum number of electrons. And then the orbit is the path by which the electrons travel around the nucleus. Electromagnetic spectrum is the range of electromagnetic properties oscillating electric and magnetic fields that travel in a vacuum with the velocity of light, which is 3 times 10 to the 8th meters per second, or 186,000 miles per second. All electrical energies move at the same velocity but differ in wavelength. The frequencies range from 10 to the 2nd power to 10 to the 24th power in hertz. The photon wavelengths range from 10 to the 7th power to 10 to the negative 16th power, all in meters. So the electromagnetic spectrum includes X-rays, gamma rays, and some non-ionizing radiation such as ultraviolet, visible, infrared, and radio waves. The electromagnetic continuum ranges from lowest to highest wavelengths, going from radio waves, which is the lowest. Radio waves, microwaves, infrared, visible, and ultraviolet, those are all non-ionizing. And then working your way up to X-rays and gamma rays, which are ionizing. Non-ionizing radiation is a special type of radiation that includes radio waves and microwaves and is not capable of removing an orbital electron from an atom with which it interacts. Now, ultraviolet light and visible light are ionizing, but only to a very few molecules. Radiation is a special type of radiation that includes alpha, beta, X-rays, and gamma rays. Ionizing radiation is any radiation capable of removing an orbital electron from an atom with which it interacts. X-rays and gamma rays are called photons. Photons have no mass, no charge, travel at the speed of light, and are considered energy disturbances in space. X-rays and gamma rays will ionize almost any molecule or atom. In this picture, you see that an alpha particle can be stopped with a piece of paper. A beta particle can be stopped with an aluminum plate. Gamma rays and X-rays can be stopped with lead or thick steel plate. And neutrons can be stopped by water or a thick slab of concrete. There are two types of ionizing radiation: particulate, which is alpha and beta, and electromagnetic, which are your gamma rays and your X-rays. And this shows you the type of radiation with the symbol, the atomic mass unit, the charge, and the origin. Take a look at particulate radiation, which is your alpha particles and your beta particles. Now, both are associated with radioactive decay, but let's take a look at alpha particles first. An alpha particle is a helium nucleus containing 2 protons and 2 neutrons. Alpha particles are very large compared to other types of radiation, but are not penetrating. Alpha particles exert a great electrostatic force. These particles have no application in diagnostic radiology. These particles are harmful if taken into the body. The most significant way people come in contact with alpha emitters is in their home, school, or place of business. Radon is a heavy gas and tends to collect in low-lying areas such as the basements. Testing for radon in your home and taking any protective action necessary is the most effective way to protect you and your family from alpha emitters. Penetration is less than a millimeter into tissue, and it's unable to penetrate a sheet of paper. Ionization accompanies alpha radiation. The energy of an alpha particle is lost quickly, and personnel monitors are not sensitive to alpha particles. Let's take a look at beta particles. Beta particle is an electron emitted from the nucleus of a radioactive atom. Once emitted from an isotope, beta particles transverse air, ionizing several hundred atoms per centimeter. The beta particle range is longer than that of the alpha particle. Penetration is several millimeters into the skin, and the beta particle is more penetrating than the alpha, but less than gamma or X-ray. Beta particles are used in nuclear medicine, and the beta particle can be used to treat health conditions such as eye and bone cancers, and are also used as tracers. Strontium-90 is the material most commonly used to produce beta particles. Beta particles are also used in quality control to test the thickness of an item, such as a piece of paper, coming through a system of rollers. Some of the beta radiation is absorbed while passing through the product. If the product is made too thick or thin, a corresponding different amount of radiation will be absorbed. A computer program monitoring the quality of the manufactured paper will then move the rollers to change the thickness of the final product. Let's take a look at electromagnetic radiation, which are your X-rays and your gamma rays. X-rays are photons produced outside the nucleus by an accelerating electron in a vacuum using a high voltage. X-rays travel at the speed of light, which is 3 times 10 to the 8th meters per second, or 186,000 miles per second. Once emitted, X-rays will ionize air. Gamma rays are photons, which are produced in the nucleus of an atom. Gamma rays travel at the speed of light, 3 times 10 to the 8th meters per second, or 186,000 miles per second. Once emitted, gamma rays are going to ionize air, and gamma rays are actually used to sterilize medical equipment and kill bacteria and insects in meat, marshmallow, and pies. Gamma rays are used to treat some types of cancer and are also used in nuclear medicine. Let's take a look at the fundamental interactions with matter. An X-ray can be attenuated. Attenuation is the absorption of the X-ray. Attenuated X-rays can be absorbed, not absorbed, or scattered. This picture here, we're seeing that an X-ray can be absorbed, and that is in an area that is radiopaque. And that means that the transfer of energy from an X-ray to matter, it refers to a tissue or material that absorbs X-rays and appears bright on a radiograph. And a great example of that is a filling in a tooth. The X-ray cannot, well, it's penetrating, but it's showing it in a different color because of the fact that some of it has stopped. So if you see something that is bright white, it means that it is radiopaque. Where an X-ray can pass through an object unaltered if it's radiolucent. This refers to a tissue or material that transmits X-rays and appears dark on a radiograph. And in the picture, you're seeing that this individual has a cyst in their tooth, and the radiation just blasts right on through it and it appears black. So let's take a look at this term ionization because we've been talking about it quite a bit. But before we talk about ionization, we have to talk about an ion. An ion is a charged particle. When a neutral atom gains or loses an electron, the electron charges of the proton no longer equals the electron. When this happens, that means that you have ionization. And ionization is a reaction in which radiation, now remember, radiation is the transport of energy through space. So it's reaction in which radiation interacts with matter. Ionization occurs when an incident ionizing radiation, X-ray or gamma ray, on passing through matter, passes close enough to an orbital electron of a target atom to transmit enough energy to the electron to remove it from the atom. The ionizing radiation may interact with and ionize additional atoms. Ionization is the removal of an electron from an atom. Ionization is the process where a neutral atom gains or loses an electron. When this occurs, the electric charges of the atoms, protons, and electrons are no longer equal. So the protons no longer equal the electrons. Ionization produces an electron with an electric charge. The charge is either positive or negative. And this is actually what happens when an X-ray occurs. So if you have a negative charge, an electron is added to a neutral atom, the electrons will now outnumber the protons, and the atom will have a negative charge. If you have a positive charge, an electron is removed from a neutral atom, and the protons now outnumber the electrons, and the atoms have a positive charge.